Picture this: Prince William Sound, Alaska. It's this pristine, gorgeous, incredibly remote wilderness, just teeming with life. And then, literally in an instant, that absolute tranquility is shattered by 11 million gallons of crude oil. 11 million. It's honestly a staggering number. And it really forces us to ask kind of a difficult question, right? When does an environmental disaster truly end? Does it end when the news cameras finally pack up and leave? When the beaches just kind of look clean to the naked eye? Or does it echo through the environment for decades?
Welcome to The Explainer, everyone. I am so thrilled you're joining us today. We are going to be exploring the ripple effect, the Exxon Valdez oil spill. Now, we're going to look at this not just as a really tragic accident, but as a profound catalyst. Because this single event, it permanently altered the entire course of environmental science, biological remediation, and even maritime engineering. It's a huge story, so let's just dive right in.
Here's our quick roadmap for today's Explainer. We're going to start with the drop, looking at the immediate disaster. Then, in the surface ripples, we'll explore the incredibly fascinating biological cleanup response. After that, the deep ripples uncovers the hidden long-term ecological consequences. And finally, the structural ripples will show us how this whole thing forced a complete mechanical redesign of modern shipping. All right, let's start at the very beginning with Part 1, the drop and the disaster at Bligh Reef. So, set the scene in your mind. It's the dark, freezing night of March 24, 1989. The conditions are calm, sure, but visibility is highly limited. Now, looking at the National Transportation Safety Board's official report, it reveals just this tragic cascade of human and systemic errors. We had a single-hulled ship navigating way outside normal lanes just to avoid icebergs. It was being piloted by a severely fatigued, completely overworked third mate. And where was the captain? Well, the captain, who had a known history of alcohol issues and had actually been drinking before the incident, wasn't even on the bridge. So when that colossal ship struck Bligh Reef, that single thin layer of steel just tore wide open and 8 of its cargo tanks ruptured instantly. And things went from bad to worse. Driven by a violent windstorm just a few days after the spill, that oil spread over 750 kilometers across the Gulf of Alaska. Guys, we're talking about over 1,000 miles of incredibly rugged coastline, completely coated in thick, toxic crude. The immediate mechanical cleanup efforts, they were chaotic. They were wildly insufficient against those freezing waters and just the sheer, mind-boggling scale of the slick. It completely devastated the local fishing economies overnight and literally left millions of animals trapped without any kind of immediate rescue. Which brings us to Part 2, the surface ripples, focusing on bioremediation and the immediate cleanup efforts. So, because of the super remote location and those freezing, churning waters, traditional mechanical skimming was practically useless. Scientists had to get creative, and they turned to microscopic solutions. Specifically, a process called biostimulation. Basically, this is the practice of adding essential nutrients to a contaminated environment to hit the gas pedal on the natural hydrocarbon-eating activity of indigenous microbes. You see, these cold Alaskan waters actually already had bacteria living in them that naturally eat oil. Who knew, right? But they were starving. So a microbiologist named Dr. Roger Prince realized something brilliant. By applying these innovative, slow-release nitrogen and phosphorus fertilizers directly to the shorelines, he could supercharge those native bacteria and artificially accelerate the natural breakdown of the oil. A real game-changer.
Okay, so how does this microscopic Pac-Man process actually work out in the field? Let's walk through it step by step, because it's pretty incredible. Step 1 is attachment. The microbes use these natural chemical compounds called biosurfactants to literally stick themselves directly onto the oil droplets. Then comes Step 2, metabolic breakdown. Once they're attached, the bacteria unleash their enzymes to actually metabolize or eat those complex hydrocarbons for energy. And finally, Step 3, mineralization. This is the magic trick where the toxic oil is completely converted into harmless carbon dioxide, water, and new microbial biomass. It was a massive success for the areas treated, proving that biology could step up and save the day where heavy machinery just felt totally short.
Now, we have to look at the darker side of the aftermath in Part 3, the deep ripples, and this spill's persistent toxic legacy.
You see, the story absolutely didn't end just because the visible oil was gone. Despite those massive, heroic cleanup efforts, the environment was hiding a pretty dark secret, one that basically shattered how we view oil spills. Up until then, the old paradigm in science basically assumed oil effects were solely short-term, meaning you get this tragic acute mortality right after the spill, the oil breaks down, and boom, it's over. But the Exxon Valdez, it forced a completely new paradigm in scientific thought. Researchers discovered a much, much darker reality. The oil was actually causing long-term chronic exposure. It was causing severe reproductive failure and triggering these delayed ecosystem cascades that nobody saw coming.
So, how did this happen? Well, it comes down to what we call subsurface reservoirs. That heavy, thick oil got trapped deep down in the coarse gravel and cobble beaches of Alaska. These rocky, heavily armored shorelines essentially acted like locked vaults. They protected the oil from the weather, from the sunlight, from the waves, basically hiding it right below the surface in this highly toxic, totally unweathered state. And the worst part? It was hiding exactly where marine life forages for food and goes to breed.
This hidden toxic persistence led to some truly heartbreaking, real-world reproductive consequences. For instance, pink salmon. Their embryos suffered incredibly high mortality rates from toxic PHHs, that's polycyclic aromatic hydrocarbons, just silently seeping into the water. This meant chronic exposure that stunted entire generations. Then you have the sea otters. They were eating clams and mussels that had filtered that contaminated water, and as a result, they experienced severe population suppression and literal multi-generational poisoning. And the harlequin ducks, because they forage right there in those shallow intertidal zones, we saw high overwinter mortality rates tied to compromised energetics that persisted for literally decades post-spill. It just fundamentally disrupted the very survival and breeding cycles of the entire ecosystem.
This brings us to our final chapter, Part 4, the structural ripples, where we look at reforming tanker design laws.
All of that biological devastation, combined with just sheer, undeniable public outrage, ended up forcing a massive mechanical and legislative revolution. Enter the Oil Pollution Act of 1990, commonly known as Open 90. Congress finally stepped in and executed a massive legislative overhaul. They mandated incredibly strict safety standards. We're talking zero-tolerance drug and alcohol policies, strict limits on crew work and rest hours to prevent the exact kind of fatigue that plagued the Exxon Valdez crew. But honestly, most importantly, it mandated the complete, mandatory phase-out of single-hulled tankers.
To really understand exactly why phasing out those single-hulled ships mattered so much, we just need to look at the engineering. Think about the single-hulled design for a second. It's exactly what it sounds like, just one single layer of steel. When the Exxon Valdez hit the reef, that one layer tore open, and boom, 11 million gallons poured out. Now look at the double-hulled design. It's essentially a ship built inside another ship. If a grounding occurs with this design, the outer hull absorbs the brute force of the impact. And yeah, it might rupture, but that inner cargo barrier, it remains completely protected, keeping the oil exactly where it belongs.
Today, this double-hull design practically minimizes major oil leakage risks by providing a vital, physical protective buffer zone. Even if it is heavily breached, the design physically restricts the total amount of oil that can actually flow out. Plus, it allows the crew to rapidly pump the cargo from a damaged tank right into the empty ballast tanks during an emergency, stopping a spill in its tracks. And because of OPE 90, this incredible design is now legally mandated for all new tankers in U.S. waters. It's pretty amazing to think that such a massive biological tragedy is what finally forced us to fundamentally change how we safely move oil across the world's oceans.
Which brings us to our final thought for today. The Exxon Valdez disaster really taught us a harsh lesson. Human error is incredibly difficult to eliminate, and Mother Nature is entirely unforgiving. Yes, we've completely revolutionized our laws. We've figured out how to harness biostimulation to aid in cleanup efforts, and we've literally surrounded our oil in double layers of thick steel. But I really want to leave you with this question to chew on. Are our current technological safeguards truly enough to prevent the next unforeseen disaster? Thank you so much for joining me on this explainer. I really hope this structured journey helped you grasp the true, lasting ripple effects of the Exxon Valdez. See you next time.